Hi, my name is Dr. Jake Herndon. I'm a mathematician from Chicago, Illinois, and the point of this video is just to talk a little bit about injections and surjections. So those are special kinds of functions. If you're studying those things, you probably already know that. But in this video, I'm going to give you 3 ways to think about injections and surjections. And in case you don't already know, I tutor online, so if you are looking for a math tutor, I'm going to put my contact info in the description of the video, so you can get in touch with me by following through there. Okay, so I mentioned this video is going to be about injections and surjections. Those are special kinds of functions, so I should just start by reminding you a little bit about functions. So a function f from a to b is an assignment of elements of a set A to elements of a set B, so that each element of the set A is assigned to a unique element of the set B. And for an element little a in the set A, we write f of little a to denote the element of the set B that the element A is assigned to. So in symbols, f is a function from a to b means for all elements A in the set A, there exists a unique element B in the set B such that f of A is equal to B. And I'm sure, as you know, when you're thinking about a function, you can think about it as having inputs and outputs. So the inputs come from the set A, and then you apply f, and you get some outputs from the set B. So like A is an input, you plug it into f, and you get some output. And the set A is called the domain of the function. The set B is called the codomain of the function. I didn't write that down, but I might use those words. All right, and for a given function, you can produce a diagram for the function. So how does that work? Given a function f from a to b, draw the set A on the left, draw the set B on the right, and then draw an arrow from this element to that element. If when you plug this element into the function f, you get this element out of the function f. So if you're studying injections and surjections, you already know all this, so I just had to say it in case you forgot. Okay, now on to injections and surjections. So like I said, these are special kinds of functions, and here are the definitions. A function f from a to b is an injection if for all a1 and a2 in the domain, if a1 does not equal a2, then f of a1 does not equal f of a2. So in other words, a function's an injection if anytime you take 2 different inputs and plug them in, you get 2 different outputs. And a function f from a to b is a surjection if for all elements b in the codomain, there is an element a in the domain such that f of a equals b. In other words, a function's a surjection if no matter what output you want to get, there's some input that gives you that output. And here are a couple example diagrams for how these functions might look. So on the left, this is an injection that's not a surjection. You can tell it's an injection because if you take 2 different elements in the domain and follow their arrows, they go to 2 different elements in the codomain. And it's not a surjection because this element does not come from any element in the domain. On the right, this is a surjection but not an injection. You can see it's a surjection because every element in the codomain has some arrow pointing to it, and it's not an injection because there are 2 different elements in the domain that get sent to the same elements in the codomain. And injections and surjections are related to each other, but when you just look at the definitions, that's not so obvious. They're actually kind of opposite concepts, and there's a few different ways to try to explain how that is. So first thing I want to do is talk about preimages. So given a function f from a to b and an element b in the codomain capital B, the preimage of the element b is the subset of the domain A, which is defined by this equation. So the preimage of the element b is the set of all the elements A such that f of A is equal to b. In other words, the preimage of a certain output is the set of all inputs that give you that output. And here's the connection to injections and surjections. So this is a fact. A function f from a to b is an injection if and only if for every element b, the number of elements in the preimage of b is less than or equal to 1. And a function f from a to b is a surjection if and only if the exact same thing, except this inequality is flipped. For all elements b in the codomain, the number of elements in the preimage of b is greater than or equal to 1. So I want to convince you that this is true. If you look at these diagrams again, this is an injection that's not a surjection. So let's go through all of these elements and just check how many things are in each preimage. How many arrows go to this point? 1. So the preimage has one thing. For this one, it's also 1. For this one, it's 0. And for this one, it's 1. So that explains this inequality. The number of things in the preimage is always less than or equal to 1. And now looking at the surjection but not injection side of this. So looking at points in the codomain, how many things are in the preimage of this element? 1. How many things are in the preimage of this element? More than 1. You got 2 here. So that explains this inequality. For everything in the codomain, the number of elements in the preimage of that thing is greater than or equal to 1. So I think this makes it a little bit more clear how surjections and injections are related. It's the exact same condition, except an inequality is flipped. All right, I also want to talk about invertibility. So this page, it's all definitions. You've probably seen them before, so I'll just go through them. For any set A, the identity function on A is the function from A to itself. That's defined by this equation. Take any input, little a, what does the function give you as the output? The exact same thing. So the identity function is the function that doesn't change any of the inputs. It just gives you that same input as the output. All right, for functions f from a to b and g from b to c, the composition of f with g is this function. You write it GOF. It goes from a to c. And it's defined like this. So GOF of a is equal to G of f of a. So it's just take an element in the domain of f, apply f. Now you're in the domain of g, so apply g. And I can say what left and right inverses are now. So given a function f from a to b, a left inverse for f is a function g that goes the other way from b to a, so that g composed with f is equal to the identity function on a. So you want to think about this as whatever f is doing, the left inverse is undoing. And so the net result is just nothing happens. And then a right inverse for f is a function h that goes from b to a, so that if you look at this composition, now h is on the right and f is on the left, you get the identity function on b. So the original function f is undoing what the right inverse h is doing. So now to tie this back to injections and surjections. So as long as the set A is not empty, this is a fact, a function f from A to B is an injection if and only if it has a left inverse. And then here's another fact. A function f from A to B is a surjection if and only if it has a right inverse. So I think, once again, this makes it a lot more clear how injections and surjections are opposites of each other. And I want to try to justify this. So I'm going to look at this diagram again. This is an injection but not a surjection. That means there has to be a left inverse for this function. So a function that goes from this set back to this set. So how do you define such a function? Okay, well, where should this element go to? This element has an arrow coming into it, so you better send it back to where it came from. And you should do that for any element that has an arrow coming into it. Just send it back to where it came from. If you've got an element where there's no arrow coming in, you can literally send it anywhere you want. It doesn't matter. So you could send this element here. You could send it here. You could send it here. You just have to pick any point. So that's how to build a function going back the other way from this set to this set. That will be a left inverse for this function. And you can also see why you need this set to be non-empty. I need some place to send this point. Okay, looking at the other half of the picture, here's a surjection that's not a injection. How do you find a right inverse for this surjection? You need to find a function that goes from this set to this set. Well, every element in the codomain already has at least one arrow coming into it. So this point only has one arrow. You should just send it back where it came from. This point has two arrows coming into it. And you can just pick wherever you want it to go. It literally doesn't matter. So if you send it here, you'll be defining a right inverse for the original function. And if you send it here, it'll be a different right inverse for the original function. So that's some justification for these facts. I don't want to prove these things in detail in the video because I think you can probably prove them on your own. And if you get stuck, they're pretty easy to find online, so I think you'll be fine. Okay, so let me summarize the point of all this. So now you've got three ways of thinking about injections and surjections. You've got the definitions. If you look at the definitions, they're saying something about what happens when you go through the function in the forward direction. You've got preimages, so that's when you want to think about going backwards through the function. And then you've got invertibility, so that's like thinking, given this function, how is it related to some other function? Like, does it have a left inverse? Does it have a right inverse? So there you have it. That's what I wanted to say about injections and surjections. So I hope that was useful for someone out there. And let me just remind you again, if you are looking for a math tutor, my contact info will be in the description. So I hope to hear from you. Bye.